Welcome viewers to the 7th lecture for the online series of lectures for the course of linear algebra. In this lecture we are going to discuss linear transformation. Let me give you the definition of a linear transformation first. For this purpose we will require two vector spaces defined over the same ground field. Let V and W be vector spaces over F. A linear transformation from the vector space V to the vector space W is a function T from V to W satisfying the following condition. T of Cu plus V is equal to C times T of U plus T of V, and this holds for all uv in the vector space V and for all scalars C. So here this multiplication is a scalar multiplication in the vector space V, because C is in the field F and we are allowed to multiply C with any vector U in the vector space V, because V is a vector space over the ground field F. And here this multiplication is the scalar multiplication in the vector space W, and we are allowed to multiply any scalar C from the field F with any vector in the vector space W, because W is again a vector space over the field F. Okay, so let me give you a few examples of a linear transformation, few examples of linear transformations. If V is any vector space over our field F, the identity transformation I defined by I acting on U spits out the same vector U for all U in the vector space V is a linear transformation from V to itself. The zero transformation, so here is another example of a linear transformation on the same vector space V. The zero transformation, which we denote by 0 hat to distinguish it from the scalar 0 in the field F. 0 hat is a map from V to itself given by 0 hat acting on any vector U is supposed to give us the 0 vector of the vector space V for all U in the vector space V. And this zero transformation is also a linear transformation. from V2 itself. Okay, so we have thus seen two examples of linear transformations on a given vector space V. Let me give you another example of a linear transformation. Example 2. Let F be any field and let calligraphic P be the vector space of polynomial functions over F. Okay, we have encountered a vector space of polynomial functions over a given field F in the previous lectures. Such a polynomial function F is given by f of x is equal to c0 plus c1x plus all the way up to ckx to the k, where all these c's are taking values in the field, that is, they are scalars. Okay, so this is a degree k polynomial over f. Now let us have a map D from the vector space calligraphic P to itself be defined by D of f is an element here in the same vector space, and that is defined in the following way. So this guy is a polynomial, and this is defined as, so the third term here is c2x squared. Okay, so we differentiate each term with respect to x, and what we get is a polynomial of degree less than the one we have here. So this is c1, this is 2c2x plus all the way up to k ckx to the k minus 1, right? So this is a k minus 1 degree polynomial over the same field f. Now I want you to verify that D is a linear transformation from P to itself. D is a linear transformation from P to itself. So this linear transformation D is called the differentiation transformation. This linear transformation is called differentiation transformation. Okay, so differentiation that we learn in calculus is actually a linear transformation from the vector space of the polynomial functions over some field F to itself. Good. Now our third example is about matrices. Example 3. In order to define this linear transformation, we should start with an m times n matrix with entries from a given field. Let A be fixed. We are not going to change this matrix. Fixed m times n matrix with entries from our field F. Okay. And now the function T from this vector space F to the n cross 1, which is the vector space of column vectors or column matrices containing n entries, where each entry of the column matrices of n times 1 column matrix takes its value in the field F. Okay, so it's a map from this vector space F to the n cross 1 to the vector space F to the m cross 1. So this is the vector space of m times 1 matrices over the field F. And this function is defined by T of u, where u is any vector here, to be equal to A times u. Remember that A is an m times n matrix, and when I multiply this m times n matrix with an n times 1 matrix here, what I get is an m times 1 matrix, which will be here, right? And this guy is naturally here. And this holds for all u in this vector space F to the n cross 1. So this function defined by this expression for all the u in F to the n cross 1 is a linear transformation from this vector space F to the n cross 1 to F to the m cross 1. Both these vector spaces are defined over the ground field F. Okay, so let me erase everything. Okay, so we had this m times n matrix given at the beginning. This m times n matrix is a matrix over the field F. Now we can refer to 1 times n matrices over the field F. Okay, which means that we are dealing with row vectors this time instead of column vectors. So and there are, say, n entries in this row vector. Such a vector space of n tuples are denoted by F to the n. Okay, so F to the n is the vector space of n tuples, where each entry of the n tuple takes its value in the field F. Okay, so you can conveniently call this F to the n cross 1 as well. Sorry, F to the 1 cross n, since it's a row vector containing n columns. You can call F to the n as F to the 1 cross n. Okay, so so our A is an m times n matrix over F. Okay, and so now we can also define a transformation U from F to the m to F to the n in the following way. U of a vector V is equal to B times this matrix A. Remember, V is a 1 times n matrix, right? So the size of this matrix is 1 times m, and the size of this guy is m times n. So the resultant matrix is of size 1 times n, so that it is indeed a transformation from F to the m to F to the n. Okay, now I leave it as an exercise for you to check that the linear transformation defined, the transformation from F to the n to F to the n defined in this way is indeed a linear transformation. Okay, so verify that U defined this way is indeed a linear transformation. Okay, good. Now a few remarks about this notion of linear transformation from a vector space to another vector space W. Remark 1. If T from a V to W is a linear transformation, then T acting on the zero vector in this vector space V, which we denote by 0 sub V, is equal to the zero vector in the vector space W, or the additive identity in the vector space W, which we denote by 0 sub W. Okay, so this is the zero vector in the vector space V, and this is the zero vector in the vector space W. The second remark is about the fact that T preserves the linear combination of vectors in the vector space V. So if T from V to W is a linear transformation, then T preserves, I'm going to explain in a while what I really mean by preserving of the linear combination, that then this linear transformation preserves linear combinations combinations. That is, now I'm explaining what it means by preserves, and that is if u1, u2, un are n vectors in the vector space V. Okay, and remember, both these vector spaces have to be defined over the same ground field F. Otherwise, none of this would make any sense. Okay, vectors in V and C1, C2, Cn are n scalars, then the linear transformation acting on this linear combination of vectors in this vector space V, C1 U1 plus C2 U2 plus all the way up to Cn a Un is going to be equal to C1 T of U1, okay, plus C2 T of U2 plus Cn T of Un. Remember that I said that it's important, it's crucial to have both the vector spaces defined over the same ground field F to have this notion of linear transformation, because you see that C1 is taking its value in the field F, and C1, the same C1 is getting multiplied with T of U1. This multiplication is the scalar multiplication in the vector space W, whereas this multiplication is the scalar multiplication in the vector space V. So if these two vector spaces are not defined over the same ground field F, we would not be able to perform these two operations at the same time. Okay, so that is the reason we need to have both the vector spaces to be defined over the same ground field F. Okay, so now we are going to number this important equation by 1. We'll have our first result by means of a theorem now, which is a very important theorem. Let me erase everything and state this theorem first, and then I'll prove it. Theorem 1. Let V be a finite dimensional vector space. We want a finite dimensional vector space so that we have a finite basis, right? Finite dimensional vector space over F and let U1, U2 all the way up to UN be an ordered basis for V. So we are choosing the dimension of the vector space V to be n. And remember the abuse of notation that we have discussed earlier in the previous lectures. This is an ordered basis. It is a set, but the ordering matters here since it's an ordered basis, although we have denoted it with a set, but you know, we mean a sequence here, so that the ordering matters. Okay, now we want another vector space W which is not necessarily finite dimensional. Let W be a vector space over the same field F, vector space over the same field F, and we need n vectors, many vectors from the vector space W, and W1, W2 all the way up to Wn be any vectors in the vector space W, then there exists a unique linear transformation T from the vector space V to the vector space W such that T acting on a basis element here in this basis set, in this ordered basis set, Tuj, okay, j can be anything from 1 to n, is equal to Wj, okay, where j is from 1 to all the way up to n. This is our equation number 2. So we are stating that such a linear transformation exists and this is unique. Okay, we cannot have two distinct linear transformations satisfying equation number 2. We'll have a unique linear transformation and that always exists. Okay, so there are two parts of the proof. One is the existence, the other one is the uniqueness. We first have to prove that such a linear transformation exists, and later we will prove that such a linear transformation is unique. Okay, let us get started with the proof. So this is the proof of existence. Let U be any vector from the finite dimensional vector space V, which has this basis, this ordered basis u1, u2 all the way up to un, and let us denote this basis by calligraphic B. Denote by calligraphic B the given ordered basis of V, given ordered basis of V. Now see that U is a vector from the vector space V, and we have chosen a basis calligraphic B, which is given by these n vectors u1, u2 all the way up to un. Hence, U has a unique coordinate matrix relative to this basis calligraphic B. Let this coordinate matrix of the vector U in V relative to the basis calligraphic B be given by x1, x2 all the way down to xn. So that what is the basis expansion of this vector? So that the in the ordered basis B, basis B, one has this basis expansion of this arbitrary vector U in the following way: x1 u1 vector plus x2 u2 vector plus all the way up to x and un vector. This is our equation number 3. Okay, good. I need room, so let me erase everything, including the statement of this theorem, Theorem 1. Now we are going to define the a transformation from V to W. Now define T from V to the vector space W by its action, the action of this linear transformation on the vector, the arbitrarily chosen vector U, on U in V, as follows. T acting on that vector U is defined as, so it's going to be a vector here that is going to be x1 w1 vector plus x2 w2 vector plus all the way up to x and wn vector. Okay, so we immediately see that this is a well-defined action, since these n tuple x1 x2 all the way up to xn, in other words the coordinate matrix of the vector u in relative to the basis b is unique. We know that a coordinate matrix, the coordinate matrix of a given vector relative to a basis, is a unique expression, and hence the same vector u cannot be mapped to two distinct vectors in the vector space W, which proves the well-definedness of this action. Okay. All right. So this is the well-definedness of this action of T on a given vector of the vector space V. Now in addition here, if we settle down with the vector U to be one of the basis vectors in the ordered basis B, so that we have U to be equal to Uj for some j in the set 1, 2 all the way up to n. If we plug it in the expression of this coordinate matrix, remember, which was given by equation number 3, xn. Okay, so if I choose U to be Uj, then the coordinate matrix of this vector is going to be 0 all the way down to 1, and then everything else is 0. So there is only one non-zero component here in this column matrix, which is 1, and that is the jth component of this coordinate matrix, which is going to be 1, right? Because when I choose U, when I choose U to be a Uj, then in that case I only survive with Xj, and that is going to be 1, and everything else is 0. Okay, so that's the jth component of the coordinate matrix, which is the only non-zero component. So then if I plug it in here, because everything else is 0 except for the jth component, then from 4 I find that T of Uj is going to be Wj, which is precisely what we want, right? According to the statement of Theorem 1. Okay, get back to the statement on Theorem 1 and you'll see that we want T to satisfy this property. Okay, so this is what we require by the statement of Theorem 1. Now we need to show that T defined this way is a linear transformation. Okay, so how do you do this? So let V be any other vector from the vector space V which have the following basis expansion in terms of the basis calligraphic B, y1, so the basis was u1 u2 all the way up to un. That's the ordered basis. y1 u1 plus y2 u2 all the way up to yn un vector. Okay, this is going to be equation number 5. This is another vector v. Okay, now we are already given this vector u, right? So that for any scalar c in F, one has cu plus v to be equal to what was u? Let me write u from equation number 3. U was x1 u1 plus x2 u2 all the way up to xn un. That was equation number 3. So from 3 and 5 one finds the expression of cu plus v, right, which is cx1 plus y1 times u1, right, plus cx2 plus y2 times u2 plus all the way up to cxn plus yn times un. Okay, now from the definition of t provided in equation number 4, we see that t of cu plus the vector v, okay, is going to be equal to this scalar multiplied with the vector w1 like we are doing here, then this scalar cx2 plus y2 multiplied with the vector w2 here, plus all the way up to cxn plus yn multiplied with this vector wn here. This follows from the straight from the definition of the operator, or sorry, the transformation t from v to w. So this is one equation. Let me number it by 6. And on the other hand, we find c times t of u. Okay, t of u is a vector in the vector space w, defined this way, and I scalar multiply c with that vector in w, because w is a vector space over f as well, and add that to the vector t of v, right, t of v in the vector space w, right. So what do we get after? So this is going to be t of u is already defined in 4, so this is c times x1 w1 vector plus x2 w2 vector all the way up to xn wn vector. That's t of u. And what is t of v? T of v then v is given by equation number 5. So t of v using equation number 4 will give us y1 w1 vector plus y2 w2 vector plus all the way up to yn wn vector. Okay, so now since we are in the vector space W, and vector space W is defined over the ground field F, we can do this: cx1 plus y1 times w1 vector plus cx2 plus y2 times w2 vector plus all the way up to cxn plus yn times wn vector. Okay, this is equation number 7. So comparing equation 6 and equation 7, we obtain the following. T of cu plus v is equal to c times the vector tu in the vector space W plus tv. Okay, this is equation number 8, and equation number 8 tells us that the transformation t from v to w is indeed linear. Okay, now we are left with proving that this linear transformation t defined by equation number 4 is indeed unique. So let us prove the uniqueness now. So we are proving uniqueness of this linear transformation. Suppose K from the vector space V to W be another linear transformation satisfying K uj vector is equal to wj vector. Okay, because we are required to have the linear transformation satisfy this property, this condition, the linear transformation acting on the basis vector uj should give us the vector wj in the vector space W. Okay, so since K is another linear transformation satisfying this property, we must have K acting on uj to be equal to wj. Okay, so for the vector for the vector u in V given by 3, what was 3? 3 was this, the basis expansion of this vector, x1 u1 vector plus x2 u2 vector plus all the way up to xn un vector. That was the vector u. And so we must have K acting on u to be equal to K x1 u1 vector, x2 u2 vector, all the way up to xn un vector. Okay, and this is equal to x1 K u1 vector plus x to k u2 vector plus all the way up to x and k un vector, and we write it using the linearity of k, since k is linear. Okay, and this is equal to because we want k of u1 to be equal to w1, this is going to be x1 w1 plus x2 w2 all the way up to x and wn. Okay, all right. So but we know that this is the same as t of u vector, right? Because the way we define t. So we end up with this expression k of u vector is the same as t of u vector, and u was an arbitrary vector, so k must be equal to t. In other words, the linear operator t that we defined by equation number 4 earlier is unique, QED. Okay, so all right, so this is good. Now we need to elucidate this this theorem 1 by means of a concrete example, which is example 4 from the lecture note that we are going to do in the second segment of the 7th lecture. Thank you for attending the first segment of the 7th lecture.